All of these observations about the action of enzymes, primarily based on the works of Adrian Brown, were formalized into a theory. And the two biochemists who were responsible for these are Leonor Michaelis and Maud Menten. So their main postulate is that enzyme catalysis occurs in two steps. The first step is the formation of what we call the enzyme substrate complex. This is a fast step and reaches a state of equilibrium, followed by a second step, which is the release of the product from the enzyme substrate complex. Furthermore, their postulate says that the overall rate of the catalysis depends on the enzyme substrate complex. And this explains the trend that we observe between the initial velocity and the substrate concentration. So if we consider very low concentrations of your substrate, then only a few molecules of your enzyme have their active site occupied. And this one is driven forward with the presence of additional substrate molecules. So as long as we add additional substrate in our system, we will have or we will observe an increase in the initial velocity. On the other end, if we have very high concentration of our substrate, essentially all of our enzyme is in the enzyme substrate complex form. We don't have the free enzyme in the system. Once a substrate is turned to the product, the active site is immediately occupied by another substrate. So we have a constant amount of enzyme substrate complex, and even if we add further the substrate molecules, we will not observe an increase in the initial velocity. Now, it is important to note that the postulates of Menten and Michaelis depends on what we call steady state theory. So in the initial stages, so after mixing your enzyme and your substrate, we have what we call a pre-steady state. So this is a process that takes place very fast, often in the microsecond scale. And what is happening is the system is focused on forming the ES complex and not on the catalytic action. So you just have a build-up of your enzyme substrate complex until you reach the steady state. In the steady state, once a substrate is transformed to its product, another substrate immediately takes its place. So it immediately occupies the empty active site, regardless of the concentration of our substrate. That is the steady state theory, meaning at any point in this graph, that is what is taking place. So an enzyme occupied by a substrate releases the product. This enzyme will immediately be occupied by a substrate. So they use this in the math that they formulated for enzyme kinetics. So now we will try to derive that equation. Again, we will start with their first postulate, which is that the catalytic action takes place in two steps. So we have the formation of the enzyme substrate complex, followed by the release of the product from the enzyme substrate complex. So again, the first step is fast and it reaches a state of equilibrium. So we use a double-headed arrow. The second step is a slow step and it doesn't reach a state of equilibrium. So we use a single-headed arrow. If you recall your general chemistry kinetics, if a chemical reaction takes place in a series of steps, the rate of the slowest step is essentially the rate of the overall reaction. So the slowest step is what we call the rate determining step. In this case, step 2 will be our rate determining step. We can also assign rate constants for each of the reaction. We can assign K1 for the forward reaction of step 1, K negative 1 for the backward reaction of step 1, and K2 for step 2. Since step 2 is our rate determining step, we can write or we can represent the initial velocity or the rate of the overall reaction as K2 times the concentration of the enzyme substrate complex. However, we cannot measure the concentration of the enzyme substrate complex real time if we try to monitor the action of the enzyme. What we can measure is the total concentration of the enzyme and the concentration of the substrate that we added to the enzyme. So we must find an expression in place of this concentration of the ES complex. So we will apply the steady state theory. So again, the steady state theory states that at any point in time, the concentration of your enzyme substrate complex is constant. This means that the rate of formation of the enzyme substrate complex is equal to its rate of consumption. So if we look back in our two steps, the forward reaction of step 1 produces ES. So we can write for the rate of formation of ES, K1 times the concentration of the free enzyme times the concentration of the substrate. The backward reaction of step 1 consumes ES. Likewise, step 2 also consumes ES. So for the rate of consumption of ES, we write K sub negative 1 times the concentration of ES plus K sub 2 times the concentration of ES. Now again, we cannot measure the concentration of the free enzyme, this E, at any point in time during the reaction. But we know the total enzyme concentration. So the total enzyme concentration is equal to the concentration of the free enzyme plus the concentration of the enzyme substrate complex at any point in time. And we know this value because this is the concentration of the enzyme that we mixed with a specific concentration of the substrate. So we can represent the concentration of the free enzyme with the total concentration of the enzyme minus the concentration of the ES. So now we have K1 times E sub T minus ES times S equals K sub negative 1 times ES plus K sub 2 times ES. So distribute S, we get two terms, K1 times E sub T times S minus K1 times ES times S equals K sub negative 1 times ES plus K2 times ES. Our goal here is to isolate ES. So if we transpose this second term to the other side, then we will have ES times K1 times S plus K sub negative 1 plus K2. And isolating ES, we have K1 times E sub T times S over K1 times S plus K sub negative 1 plus K2. So we can factor out Ks in the denominator. So we have the concentration of the substrate plus K sub negative 1 plus K2 all over K1. And we can cancel out K1. And if we represent K negative 1 plus K2 over K1 with another constant, let's say K sub M, then we will have ES equals E sub T times S over S plus K sub M. So now we have an expression for the concentration of the enzyme substrate complex, and we have variables here that we can measure. So we substitute this for ES. So we have initial velocity equals K2 times the total concentration of the enzyme times the concentration of the substrate over concentration of substrate plus the constant Km, and the Vmax that we saw a while ago, this is if all of your free enzyme, so at Vmax, all of your free enzyme, or essentially the total amount of your enzyme, is just the amount or the concentration of your enzyme substrate complex. So this is in the right side of the graph. So if we have this expression where v naught or initial velocity is v max, then we can represent v max as K2 times the total concentration of the enzyme, and we can replace this with v max. So we have initial velocity equals v max times concentration of substrate over concentration of substrate times the constant Km. And this constant is the Michaelis Menten constant.